Hi, it's me again. For this week, our lesson is going to continue on with the gradient function. Last week, we used the gradient function to find the instantaneous rate of change at a point on a curve, and that's what I said here. Using it in this manner, what we find out is what is the speed of a toy rocket at 12 seconds. So this is an example just to give you an idea of how you can use it in context. And I used the toy rocket example in my Zoom meeting of a couple of weeks ago, which was also posted on last week's summary of April 30th meeting if you want to review that. So the toy rocket example is what I'm going to continue with. The gradient function will tell me the speed based on time. There's another great way to use a gradient function. You can use a gradient function in the reverse. You can use it to find the coordinates of the point on the graph. So instead of already knowing the x value and finding the speed, we know the speed and we want to find the x value. This is valuable because it could answer questions like this. At what time was a toy rocket speed 12 meters per second? So we know the gradient, we know the instantaneous rate of change, but we don't know the time. Or we could ask the question, how high was the toy rocket while going 12 meters per second? Again, we know the rate of change, but we don't know the height. So in order to do this, we're going to need several things. The first thing we're going to need to know is the original function. And the original function of that toy rocket's trajectory is this. And it is what this says is that the height of the rocket is based on the time passed. We also are going to need to know the gradient function of that rocket. And the gradient function of that rocket says the rate or the instantaneous rate of change, the speed of the rocket, is dependent upon the time passed. And then the last thing we need to know, and I want to do this different. The last thing we need to know is the speed at a given time. In this case, I'm going to use 12 meters per second. So I'm starting off the problem with a speed. And once you start off with the problem with the speed, you're going to use a gradient function still, and you should think, oh, rate of change, speed, I'm going to use a gradient function. I'm going to show you how to use the gradient function to answer the question, at what time was the toy rocket speed 12 meters high? So we are solving for t here. And since I already know the instantaneous rate of change, I'm going to start with the gradient function. So let's use the gradient function. And you can see that function up here, the green highlighted one. H of t is equal to 37 minus 2t. The speed of the rocket is based on the time. So you can't ever solve an equation unless you only have one variable. Here I have two variables. This whole dependent is a variable, and you have the variable t, and we're solving for t. So since we're solving for t, we're given a number, we're given 12. And if you think, oh, I'm solving for t, I must have to substitute 12 for the speed. And the speed in this function is the output. So h prime t represents the speed. So if the speed is 12, I'm going to substitute it at 12 meters per second. What time was that? And now we just solve by using inverse operations. So we say negative 37 minus 37. You know, once I get to this stage, my higher level students just love it because it is solving a two-step equation, which we've been doing probably since 8th grade. So I don't think I need to talk because I think you know what I'm doing. So then t equals negative 25 divided by negative 2, which is 12. I'm going to make that a 12. That looks funny. 12.5. I made a mistake there. Surprise, surprise. Okay, so the question was at what time? So it was our t. Our t was 12.5. Was the toy rocket speed 12 meters per second? So I'm going to answer the question just in the same way. I would say at 12.5 seconds, the toy rocket speed was 12 meters per second. And so that's how you find the time. Notice it's just giving a different variable. You knew the speed, you didn't know the time. What we did last week is we knew the time and we wanted to get the speed. So that was the first question that we answered. The second question with this problem that we want to answer is how high was the toy rocket when it was going 12 meters per second? And once again, we're talking, we got to figure out what function. I make a big deal about the two different functions we have here. We have the original function that relates the height of the rocket with the time. We have the gradient function that relates the speed of the rocket with the time. In this case, we're looking for the height of the rocket. So would you use the gradient function again, or would you use the original function? You would use the original function because the original function relates the rocket's height to the time. So the original function is h of t is equal to 37t minus t squared. And we already know the t value. We know that at 12 meters per second, the time was 12.5. So we're going to take this. That is the time. And we're going to substitute 12.5 seconds for t because we know the time. So h of 12.5, the height of the rocket at 12.5 seconds, that's what this statement means, is equal to 37 times 12.5 minus 12.5 squared. I put parentheses around it because the negative does not belong in the parentheses. That would come out with a totally different answer. So now we just simplify. We are not solving anymore, we are simplifying. So h of 12.5 is equal to 37. I did the math ahead of time so I don't mess up. 37 times 12.5 is 462.5 minus 12.5 squared is 156.25. Simplifying it even further, you subtract 462.5 and 156.25 and you get 306.25. So let's go back to our question. What was it asking? How high? So how high was this h of t? That's what we were solving for. And we weren't really solving, we were evaluating. We say solve when we have to do inverse operations because we want to find the value of a specific variable. We say simplify when we want to simplify. We also say evaluate when we know a variable and we want to find the other one. So let's write this in a sentence that reflects the question. How high? So I'm going to say it different. The rocket, the toy rocket, was 306.25 meters high while going 12 meters per second. And that's using a word problem, that is how you can use the gradient function to find not, if we already know the speed, then we can use a gradient function to back into the ordered pair that is represented by that speed. Now, this is the graph that we had in the presentation lab in my Zoom meeting 2 weeks ago. And you can't see it very well, but this is 12.5, 306.25. That's what we just figured out. And the speed at this point was 12 meters per second. And what I want you to relate is the very first thing we did when we were looking at this whole speed and rate of change of a curve was really, really confusing. And I had you match a point on a graph with an approximate rate of change or gradient. This will kind of now give it more meaning, I hope. In this lesson that I did, at 28 seconds, the rocket was 252 feet high, and that was at 19. That speed was 19 meters per second. And the other point I have is at 10 seconds, the rocket was 270 meters high, and the rate of change was 17 meters per second. Now, I'm showing you this because I want to make some sense of it. If at this point the rocket was going 17 meters per second, I would expect it to go slower, at a slower speed here, because the differential between these two is not that great. This point here is on a flatter part, relatively flatter part of the curve when you compare it to that. So that makes sense to me. And then looking down here, this 19 meters per second looks a tiny bit lower than the 17 meters per second. So that means at this point on the curve, it's a relatively steeper part of the curve than the 17 meters per second. And so hopefully that ties it together with the very, very first lesson that we went into that was probably the most confusing. So the kind of problems you're going to do this week, let me show you. We're going to do some examples. And I know this video is going to run long. You can stop it and start it as many times as you want. So let's go on. Okay, so these are some of the problems that if you were taking the IB exam, you would see. It says, point P lies on a curve. So this is our original function. The gradient of the curve is this. So this we found as our gradient. And I'm going to use this expression because you'll see why. Okay, is equal to 7. So find the coordinates of P. Same thing. First step is find the gradient function. You need to know the gradient function. And I probably won't explain it too much because we've done a lot of it. At least I feel like we've done a lot of it. I will kind of walk through it, but I won't explain it in detail. So the gradient function, we're first going to give it a different name, d of y over d of x. That's why I showed that there. Equals, and we'll do the power rule. 2 times the coefficient of 1 is 2x. Then 2 minus 1 is to the power of 1. So I'll do it here so you know what I did. And then 3x is 3 times x to the power of 1. So 1 times 3 is 3x. It's not. It's 3 because I have to subtract 1 from that 1. And so that becomes x to the 0, which is 0. And then again, remember this x doesn't ever show up because x to the power of 0 is always 1. But in this case, I'm going to say 0 times negative 4 is 0, and that's why it's not showing up. So what we do next, now that we have the gradient function, we're going to substitute. It's the exact steps we were doing on the other page. Substitute 7 for d of y over d of x. That is the rate of change. Last step is we're going to solve for x. And this is going to tell us the x coordinate. So to solve for x, we're going to subtract 3. And then you get 2x equals 4. Divide by 2. So the x coordinate of point P is 2. So if I were to let me write my answer here. So point P is 2 comma, we're missing one. What are we missing? We're missing this y value. To find the y value, it's like finding the height of the rocket on the last example. We have to use the original function. Because remember, the original function is what relates x and y. And that original function is y equals x squared plus 3x minus 4. So using that original function, we're going to substitute. I almost feel like I'm in class. 2 for x. I feel like I'm almost in class because I'm running out of room like I've done in class many, many times. So we're substituting 2 for x. So 2 squared plus 3 times 2 minus 4. And then we're going to simplify. So y equals 2 squared is 4, plus 3 times 2 is 6, minus 4. 4 plus 6 minus 4 is 6. And that's your answer. Now, we don't have any words along with it, and that's fine. I think that's why math gets hard, though, because you can't even reason out the context because there's no words. But let's do it again. A little bit different wording, same thing. It says find the coordinates of the point on the curve y equals 3x squared plus x minus 5, at which the gradient of the curve is 4. As soon as you see that they gave you the gradient of the curve, you know you're going to use the gradient. So you're going to use the gradient function first. So we have to find the gradient function. Again, you're going to say the first term is 2 times 3. So we name the gradient function a different name. 2 times 3 is 6x. Now we have to subtract the 1 from there. So 6x to the first power, and I'll just put it there so you know what I did. Plus, this term here is a 1x to the first power. So we're going to multiply 1 times 1. 1 times 1 is 1, so we get 1. Now, do we need an x or not? We're going to say minus 1, so that becomes 0. So it's just 1. And remember, this one here is negative 5. Our last term is negative 5x to the 0. Multiply 0 times 5, you get 0. So we have our gradient function. Same step as we did in problem number 1. You're going to substitute. What's our gradient here? 4 for d of y over d of x. And I don't know why I'm getting so crowded. I have plenty of room. So 4 equals 6x plus 1. And then you're going to simplify. What am I doing? Subtract 1. Because I said simplify and I was totally incorrect. This one's called solve because we want to find the value of a variable. We don't know it. So minus 1 minus 1. Just like in class, I make mistakes. I don't edit these. I do it just like I'm in class. And we just pray for the best. Many of you guys are going to say, Mrs. Sharillo, really? A fraction? Yeah, but guess what? I'm going to write it as a decimal. What's 3 over 6? It is 0.5. Okay? So if you don't like the fraction, if it's a terminating decimal like 1/2, use it. Okay, so what? We found that x was 1/2. So our first is that. Why I write this ordered pair here is so you guys can say, there's something missing. What's missing? Well, Mrs. Sharillo, it's find the y value. And remember the y value is based on the x value, and they're tied together by the original function. So you use your original function, which is y equals 3x squared plus x minus 5. Next step, we want to know what y is. Substitute. What was our x value? 0.5. We want to substitute 0.5 for x. I'm not writing for x because I ran out of room. So 0.5 squared plus 0.5 minus 5. I even ran out of room for the zeros. So and now you're going to simplify. You don't need to solve, we just simplify. So y equals 3.5 times 0.5 is 0.25. We have to square it first. Plus 0.5 minus 5. So 3/4, 3 times 0.25 is like I have 3/4 in my pocket. That's 0.75 plus 0.5 minus 5. You guys with me? So now if I did my math right, which I'm double checking because I always doubt myself, 0.75 plus 0.5 is 1.25 minus 5, and you get negative 3.75. So our y equals negative 3.75, and you are done. Okay? So these two problems started out with the original function being a quadratic, meaning the highest power was 2. So then when you did the derivative, it became a linear function because the derivative is always 1 power less than your original function. Let's step it up a bit, a little bit more complicated. Now we say there are 2 points. Oh my goodness. There are 2 points on the curve y equals x to the third. That's a mess. Minus 6x plus 1, at which the gradient of the curve, again, you see gradient of the curve is 6. Find the coordinates of these 2 points. So the first 2 problems we just finished, we only found 1 point, but you do it the exact same way. So the first thing you're going to do is find the gradient function. And this is a y equals again, so I'm going to say dy over dx equals, and let's do the power rule. I won't do all the markings. 3 times 1 is 3. The exponent is 3 minus 1 is 2. Minus 6, remember there is 1 really up there. Negative 6 times 1 is negative 6. 1 minus 1 is 0. And again, the constant just goes to 0. Then you're going to substitute the gradient. The gradient is 6. So we're going to put 6 here. Now, it asks for 2 ordered pairs. Does anyone know why we're going to come up with 2 answers? Anyone? If you don't, I'm going to gently remind you, of course, as soon as this gets back into focus. Okay. That's because in a quadratic, most times, not all the time, you can have 2 real solutions. So seeing this quadratic, I don't see an x term. I don't see a middle term. So I'm going to solve now, but I'm going to solve by taking square roots. And again, we're going to do the inverse operations. We want to get that x by itself. So the first thing you look at is, let's say, plus 6. Something is totally wrong with this. Minus 6. What did I do wrong? Oh, I know why. Guess what? This is a typo. This typo should say negative 3. So let's make this negative 3. Now you really feel like you're in class, for those of you who really can't stand my mistakes. So we're going to say plus 6 and plus 6. Although that would have been an easier equation, it could have been 0. I should have just left it. So negative 3 plus 6 is a positive 3 equals 3x squared. Divide by 3 first, because you have to get you've got to do reverse order of operations. Addition, subtraction first, multiplication, division next, then you deal with the exponent. So now you have x squared equals 1. Then you're going to take the square root of both sides, and hopefully you notice that plus or minus right there. So now you have x equals plus or minus 1. So we are going to have 2 points. We're going to have point 1, which is a positive 1, and we're going to have another point, which is a negative 1. So remember, now we have to find the y values, and there's 2 of them, so we're going to have to do it twice. So find the y value when x equals 1. We'll do that first. So original function, y equals x to the third minus 6x plus 1. Substitute x equals 1. So y equals 1 to the third minus 6 times 1 plus 1. Y equals 1 minus 6 plus 1. So y equals 4. That's the first one. Now you have to find the y value when x equals negative 1. And you guys know it will not be the same number. Original function, y equals x to the third minus 6x plus 1. Substitute negative 1. So y equals negative 1 to the third minus 6 times negative 1 plus 1. Since this is negative 1 times negative 1 times negative 1, that's a negative 1. And a negative 6 times a negative 1 is a positive 6. Negative 1, positive 1 cancel each other out. So y is 6, and that's your final answer. And that's what we're going to do this week. And hopefully you guys won't have too many questions, but if you do, you know how to get in touch with me. And I apologize for that mistake there. Thank goodness you guys are the only ones seeing this video. Take care. Bye.